let's talk about PDF.js. First of all, thank you all for coming here. I know that I'm competing with Paul downstairs, so I'm amazed as many people came here. I would be in Paul's talk right now, but I have to give the talk right now. So my name is Andreas. I work with Mozilla, and this work I'm presenting today was made by now something like 15 contributors that are not all on the slide. One person that is on the slide is Julian, who actually made the slides for me. He's also one of the PDF.js authors, so Julian, raise your hand. Hi, Julian. Yeah, please thank Julian. You don't have to look at this kind of slides I usually make. That's a big plus. So I'm going to talk a little bit about PDF rendering and about the structure of PDF and how we do this in PDF.js, about images and fonts. But also I'm going to spend quite a bit of time on the problems we encountered, and then also actual performance problems we ran into. And I want to kind of show you what kind of things are really important to optimize if you are looking at a system like this. And then I will conclude with a to-do and the to-do list for PDF.js and the obligatory demo. So the goal of the PDF.js project was to produce a faithful, high-quality, fast, efficient PDF renderer. And by the time we started this project, really the motivation for us was to find out whether it's possible to use the HTML JavaScript platform to build a PDF renderer. At that point, there were a couple kind of like toy PDF renderers for a tiny subset, or maybe you can like draw a figure with PDF-like rendering commands, but no actual PDF renderer. And all browsers at that point were using native code to do PDF rendering. So Chrome, for example, embeds this like commercial Foxit PDF renderer. And we were just wondering why it's not being done in JavaScript. We wanted to find out. And personally, I'm not really a web author. I'm a platform engineer. I make browser platforms. And I was curious whether there are things in a platform that somehow prohibit you. Maybe it's too slow, or features are missing. So it was more an experiment in browser technology, really, than PDF rendering. And really, the main goal from this perspective, being a browser implementer, is we wanted to avoid having native code in the platform. A former VP engineering of Mozilla affectionately calls the Acrobat Reader a popular native code execution format. Every time you put native code into a browser, there's always a risk that it can get exploited, and PDF readers have been exploited in the past intensively. So the last major iPhone exploit was based on the PDF reader in the iPhone itself. So using the web to build these pieces gives us a secure platform where you can run PDF documents and display them, and you don't really risk being taken advantage of. So let's look at PDF format. PDF is a document format. It looks very similar to other document formats like Word documents. There's a header that tells you a little bit about the PDF version. And there's an actual body that contains streamed objects that are identified by a position into the file. And this builds basically an object graph that consists of the different pages that are linked together to a document, and individual pages have rendering commands and images and so on. And then at the end of documents, there's a table, the xref table, and this provides quick mapping of object IDs to indexes into the file. So this is what you use to actually find individual objects in this large file. And these files can be large, hundreds of megabytes, so it's really important to have a central point where you can find them. And then the trailer at the very end of the file kind of tells you how you can find to the root of this object tree. And when this PDF format was specified many, many years ago, it's kind of predated really exchanging data over the wire. So this format is actually not very suitable to actually be transferred, because you have to basically fetch the entire file all the way to the last byte before you can display any single page. So by now there are a couple additional extensions to this format where you can only just fetch subparts of it and stuff like that. So there are slight complications on top of this, but this is the basic structure. The way we are processing this is we're currently loading the entire file with XHR into an array, but we can also support very easily this idea of having range requests only get parts of the file, so you can quickly render these things. And you create a PDF document object around that, and you can fetch pages from that document. And there are these two stages to rendering. First, we start the rendering by providing a graphics context and the page. And this is going to go and read all the objects associated with that page, which contains of rendering objects and images. And it's going to process all of them to identify resources we have to load before we can actually display the page. And then once those resources have been loaded, in particular fonts and images, then we can actually execute this sequence of commands that we have just recorded for the page. This is important because in a general HTML page, when you apply some custom font via CSS, then if the CSS rule takes a moment to load, we can just go ahead and render the page with the wrong font, and the browser automatically is going to re-render the page as soon as the actual CSS rule and the font is available. For Canvas, unfortunately, this is not being done. So if you set a new font on canvas and don't wait for the browser to load it and start drawing, you just get the bad font in there and that's it. So to avoid that, basically that's why we record these PDF commands first and then load the font, and once the font is loaded, then we actually display the page. So here's an example of a PDF file and an object from this kind of PDF file. So object number 3 is a page in this PDF document, and it has really two important parts. One is the resource part, where fonts and graphic objects are in, and then contents is the actual command stream that renders a PDF document. So initially we fetch the object number 3 if you say get page, and then if you start rendering, we have to fetch the resources and the actual content and parse those further. And this is what the actual content stream of this page here looks like. It's a sequence of commands here. Stream is kind of Adobe's way of saying array. So it's really just an array of commands that execute in sequence. And there's various different commands here. The first one sets the graphic state. The second one is F0 there. That's a font command. It says select font 0. And then you can see actual text drawing commands in the middle part of it. And if you were to look at a PDF document in a text editor and it's not encrypted and it's not compressed, you would actually literally see this text here. So it's a text-based format. However, to achieve better, to achieve small documents, frequently this is actually compressed with zip. So basically this stream part is then taken and compressed with a simple deflate algorithm. So in this first step where we collect all the resources, we walk the XRF catalog and find all these different fonts and anything else we need. And in parallel, we build an intermediate presentation that contains all the rendering commands that we encounter. And again, we cannot execute them yet because we have not loaded all the resources associated with it. So you can see here that we set a graphic state, and then we notice dependency. And this one actually goes off and fires off a custom CSS rule that attaches to the document to load the font. And the set font command here cannot be executed yet. We are just storing this in an array. As soon as the actual font loading is complete, then we can execute this sequence. And the rest of the IR looks pretty much like a Canvas interface. So Canvas is currently the backend we're using, and it's roughly the same commands that are also in Canvas. The one minor difference is that we actually keep track of the state of a cursor when text is outputted. So not everything in PDF is absolute positioned. Actual text, you have to measure how long the word is, and then position a cursor there, since there might be more text showing up without an extra positioning. So once then all the fonts are loaded, then we can actually go ahead and execute a sequence of commands, and all the fonts will be available, and all the images will be available, and we can draw them to a canvas, and that's it. Images. So PDF documents can contain a bunch of different image formats. There's something like 8 or 9 different ones. A pretty common one is JPEG. And when we first started this, we did a little experiment of implementing JPEG just in JavaScript. And it turned out to be really, really slow. Something like 10 to 100x slower, depending on what exactly the JPEG file looked like. So what we ended up doing instead is, since the format is also natively supported by the browser, we just take the contents of the file and base64 encode it, and then stick it back into a DOM element that does the actual decoding work for us. And if it's not a JPEG stream, then we have to do the manual decoding by hand. There's a bunch of different formats you have to do that for. So PNG, for example, can appear in PDFs. Unfortunately, the PNG format that Adobe uses is not exactly the way the PNG standard looks like. So there's a couple of different things in there. I'm not sure Adobe can be blamed for this. So I think by the time they did this, the standard was not entirely passed yet. So Adobe kind of like snapshotted a version of it, and then that ended up not being what's really the standard. So PNG we have to do by hand. It's a pretty efficient file format, so it's not very difficult to do that. There's like just bitmap compression formats and so on. What you do there, basically, just read the data, we convert it to a color space, and then use Canvas and just blit the pixel data in there. So most of this tends to be pretty efficient. Fonts. So PDF documents can contain a bunch of different font formats. There's type 1 fonts, type 2 fonts, type 3 fonts, and the casual observer might think that these are like supersets, right? Like type 2 is a superset of type 1, and then type 3 is a superset of type 2, and that's the furthest thing from the truth. So type 1 and type 2 are supersets and subsets of each other. And you cannot convert trivially either one into the other, but you can do some tricks. So type 1 fonts actually not support on the web. Type 2 fonts are, since you can convert it to OpenType. So what we end up doing is we take type 1 fonts and kind of reinterpret them. We interpret the sequence of commands that draws the outline of the font, and emit the equivalent type 2 instructions for that, and convert all the hinting data, and then get a type 2 font out of that. And a type 2 font we can wrap into an OpenType font container, and then that the browser can load. And then we use a custom CSS rule that we inject in the document to actually load the font as we are parsing through the document. Unfortunately, some fonts cannot be converted this way. So type 3 fonts, they even go a step further. So in this type 3 font, every glyph is a PDF document. So in theory, for every glyph, you can have a video playing in there and a little Flash running and everything else craziness you can do in PDF. So type 3 fonts, you cannot convert this easily. Basically, what we are planning to do there is to simply use the rendering pipeline we already have to draw each individual glyph. It's going to be horribly slow. Fantastically, type 3 fonts are almost never used, so it's not really a practical problem. All right, so this is kind of the nice part. So far, everything's worked, everything's great, everything is fast. Let's talk about the problems we ran into. And there were quite a few. So there's currently in the browser no way to detect that a font is loaded. I explained this before on Canvas, that if you just specify a new font and start drawing with it, you're going to have the wrong font until the font actually loads. So there's no way to get notified right now. That's, of course, kind of like really ugly. So what we ended up doing is you can detect it kind of by indirection. So you can set yourself a timeout that's going to call you back all the time, and you're waiting for the font to load. And you can take a little 1-pixel canvas and put the font in there and then measure its width. And if the font loads, eventually the width is going to change. So then you know the font has been loaded. Of course, this is not a particularly efficient way of doing these things. So that's a nice thing when you're working for a company that makes a browser. So we can talk to the guys who do these things. And we already proposed, in addition to HTML5, to allow you to have an event when actual font loading is complete on the canvas. Another kind of random problem I ran into was actual font measurement. So I explained before that in PDF, not every command is absolute positioned. In case of text, you're supposed to measure the width of the text and then continue after that. And this overlaps sometimes absolute positioning as well. So it's very important to do very precise font measurements. And it turns out if you measure with Canvas fonts on many different browsers, including ours, you get kind of like results that are a little bit off by a couple of pixels. But that's enough for like your fonts kind of glue into each other and looks really crappy. And we realized that this is a rounding error that happens in many font implementations. So many browsers tend to use the same font engines, and they have certain rounding errors that are being used by PDF. And we ended up doing a very gross hack that I will come back to. At the end of the talk, I can show you what it looks like to kind of work around these kind of things. Subclass fonts look very different in individual platforms. It looks different from operating system to operating system, different from like version of the OS to the, really depending how Canvas draws. So on more modern platforms like macOS and the recent version of Windows looks pretty good, but if you go back to Windows XP, you can look on your own. Text selection doesn't really work very well for us right now. We're using Canvas as a backend, so you're exploring other options there, using SVG, for example, where text selection is a little bit easier to do than on Canvas. Printing is the same. We're using right now a fixed size canvas. If you print that, it's really going to look like crap because we are pixelating at a much lower resolution. This is mostly, again, an API problem. There's no terribly good APIs right now on the web to print. So we filed a bug, and this is something we want to fix. So there should be a much more efficient way how you can communicate print commands. For example, you could have a print canvas. Where you can say, OK, I want to print, give me a canvas, I will do print commands on it, and the browser can figure out how to translate that to your local printer. And the performance, of course, is a problem. I'm going to talk about that a little bit more in a second. When doing this project, this was basically my first really large JavaScript project. I'm not a JavaScript web author. I do browsers for a living. So when we started doing this, it was very important for us to have very nice maintainable code because we're not very good JavaScript hackers. So we want to make sure everything's really extensible, people can understand it. We started the project straight on GitHub. So we want to make sure people can actually help us and help out, just community contributors. So we really tried to write very nice, stylized, modular code. That's great. However, in some cases, it also has to be really fast. So if you're sitting somewhere deep in an image decoder, we have to make really sure it's very fast and efficient. Otherwise, we're just simply not competitive with a native code PDF reader. And that was really the goal. We wanted to see that you can use JavaScript to be as efficient as the native code implementations. So just a couple of things that we kind of run into in optimizing observations, more or less. This piece of code here is the actual deflate algorithm that goes ahead and decompresses the PDF command stream that comes in as a text file. And first wrote the nice modular version was way too slow to be used. And I used the profiler then to kind of go ahead and find out where the problems are. One of the first things I optimized is that this little function there, ensure buffer, what it does every time you're decoding more data from the compressed file, you have to make sure you can write to your output buffer. And this ensure buffer makes sure basically there's enough room to write another character. And I used to call this straight directly from the code. And it turns out this function call is just way too expensive. There are too many characters. These files are large, hundreds of megabytes. You make way too many function calls, really slow. So instead, what you end up doing is you just kind of pulled that if condition out of there, and we only conditionally call it if the buffer needs to be extended. And that was a pretty substantial speed up. At the same time, it's important that you don't go overboard. So this kind of inlining makes sense where it's really performance critical, and it's a very thin function. You don't want to go overboard and completely stop using functions because your code looks totally unreadable. So this get code here, that's actually a very substantial amount of code that I use several times in this function. If I take that apart everywhere, then the code is really long and unreadable. And there, the function call overhead is much less in comparison to what happens in the function. So that one we didn't touch. And then similarly, we had little helper functions around this code 1, shift right to 16. You can't afford in this kind of performance critical code calling any kind of helper functions. And it's also important the way we represent data here. So this length decode is an array. It contains data. And it contains really two different things, a length and a code. And initially, we used to have an array in there, these two indexes, index 0, index 1 for data and length. And this additional array lookup was also pretty expensive. So we just kind of munched those two numbers together and shifted them together. And that got us another 50% or so speed improvement. So it's very important that when you have critical code, after you've written it in a nice way, you can go ahead and optimize it. And you really only do that for the critical parts of your code. Something else that I was talking about earlier is that we're using the internal JPEG decoder in the browser, and that's really important. JPEG is a very complex format. It's a lot of complex math going on to decode it. You do not want to write it in JavaScript. Unfortunately, we are under the same problem here as with PNG, that Adobe's implementation of JPEG subtly differs from the way it's implemented on the web. In particular, there's something wrong with color space conversion. So actually, here the web is wrong. On the web, the way JPEGs are displayed is the way Photoshop generates them, not the way the standards say. And you can't really change that because so many images are made by Photoshop. And in PDF, the format is used correctly, the way the spec wants it to be used. And unfortunately, they're incompatible. So if you try to render the document, the PDF JPEG, you get completely wrong color space. So what we ended up doing, we kind of munch the JPEG file. We read it, we insert a little header that the browser knows about and choose a different color space. And then we load that newly rewritten JPEG file into the browser. And that made that work. Last but not least, I want to talk a little bit about the way we generate all these data streams. So we have frequently what we do in PDF.js, we read data and then write out data into a file again, or a buffer, and then load it into the browser. And the first naive implementation that someone from the team did looks roughly like this here. You get the stream data as a bunch of bytes, and then you have a little write function that you give an array of data, and it goes through that with a for in loop, and pushes into a new font array where all the new font data is collected. And then down there is kind of roughly what the font loop looked like. There's some data we pull out of there, and we write 2 bytes, for example, to the file. And this was horribly slow, and for many different reasons. And just to enumerate a couple of them. So for in arrays, if you do a for in loop over an array, and the indexes have to be stringified in the for in loop. So I in this array, in this loop over this array, is always a string by the specification. So we have to take these numeric indexes 0 and 1 and stringify them all the time. And that's a pretty substantial cost. So you want to avoid for in loops over arrays. The next thing is the actual push on an array to store data is not a particularly good idea. That's really expensive. You have to call this native push method. You have to extend the array every time. So that turned out pretty expensive. Down here, to write out the data, he created a new array around it every time. And modern GCs can take care of the trash you're generating here in this loop, but just making that object is pretty expensive. So you're kind of using up a lot of cache space there and hardware just to make all these little arrays. And last but not least, also calling this function here that almost does nothing is a pretty big overhead. So after optimizing all these things, the font loading code got substantially faster. And after optimizing that, I got pretty curious, what is actually really the fastest way in a browser to write into a variable size buffer? And to my surprise, actually, it's strings. And that's really weird, because strings are not even 8-byte arrays. They're really 16-bit arrays. So basically, what we ended up doing in the current code base now is that we start a string out empty and then concatenate characters in there using from char code. And if you have any constants we have to write in there, we just use this hex string notation to write it in. And the best explanation I can give you for that, why strings are so efficient in browsers, is that they're highly optimized for benchmarks. So kind of pre-SunSpider, this very popular, terrible JavaScript benchmark, people used to avoid string concatenation because it was terribly slow in IE6. Now we're in a post-SunSpider world, and SunSpider does a lot of string concatenation. So today, every browser is deeply optimized for concatenating strings. So now it's a really cheap operation. So if you want to do something really fast, what you have to do, you have to make a benchmark, and then everyone's going to optimize for it. All right. Last but not least, typed arrays turned out to be also a really important performance feature for us. So we switched all our array use to typed arrays the best we can. And that gives you a nice speed up. And even for literal, it's just like tables of data. It's actually very efficient to do that. It's often also more compact. So this is, for example, a 32-bit array of 32-bit integers. And it's just much more compact to represent it as a typed array. Because a regular array needs larger data entities that store the type and the value. And in these typed arrays, everything is the same type. Unfortunately, for typed arrays, you can't form easily literals around them. So what we did, we basically make a regular array that you can initialize as a literal, and then just wrap a typed array all around it. And for a brief moment, you have the full array in memory, but then it gets replaced with a typed array. Of course, in some browsers, you don't have typed arrays. As we're doing the slides, Opera, Safari Mobile, and IE9 don't have them yet, as far as I can tell. In that case, we just emulated typed arrays for using traditional arrays. And their API is roughly compatible. So basically, on these browsers, it works with a little emulation layer in between. It's just much lower. Really, what I was trying to encourage with a couple slides previously here is I encourage you to use profilers. We really found them extremely useful in our code base. You go ahead and you write your code as nicely as you can, and you grab a profiler, and you kind of knock off the top like 5 or 6 performance problems you can find. And that basically has already taken care of the majority of the performance you can squeeze out of the program. So you can have it kind of both. You can have a very nice modular code, and at the same time, it can also be very efficient. And some of this stuff is really subtle. It's very hard to tell. So when we started, I always found the type-off syntax really confusing. So I like to avoid it like the plague, and I wrote myself with little helper functions like isNum that's going to tell me whether a value is a number. And we use this very consistently through the code base. And one of the things that profiler highlighted as I was going through the code base is that in this little loop here, where data is being processed and rewritten, I used isNum to check whether the value I was getting back is a valid byte, or actually I've reached the end of the file, in which case I think undefined is coming back. And this function call to isNum was the majority of the cost of this loop here. Something like 90% of the time was being spent calling the isNum function, not even inside the isNum function, just calling it. So a profiler can very easily kind of highlight these things, and there's various different ones. The Firebug is available for Firefox, and WebKit-based browsers have a profiler built in. So you can very nicely identify that's a problem. You can just take the guts of the function, inline it, and you have eliminated the overhead for the call there. And that really, this goes a long way. So you sacrifice a little bit of beauty there, you fix a couple places up, and they're not as nice as you would prefer to write them, but you get really dramatic performance improvements. The last but not least, DOM calls. We also ran into quite a few problems just this DOM calls being slow. And the reason for that is that JavaScript has a different representation for objects than most implementations of browsers, which are usually in C++. So even JavaScript, you have a JavaScript string, a JavaScript object, and C++ has this like C strings and C++ objects. So whenever you call into the DOM, you have to take those JavaScript objects, return into the C++ objects, and then the DOM does some processing on it, and then it returns the data, which you have to, again, convert back. And really, the only way to make that fast is to not do that. Do not call in the DOM if you at all can avoid it. So in this case here, we just wrapped a little cache around measure text. So whenever we measure text for the same font, for the same text and the same size, then we just don't hit the DOM again. We put in a little cache on the JavaScript side, and everything gets much, much faster. And this is particularly useful for re-rendering. So when I show the demo in a second, you will see that the second time you go across the page, it's very, very fast. It's instant, because nothing has to be really measured anymore. And something else that's visible on the slide here is this little ugly hack I was talking about. So I mentioned to you that many browsers don't measure fonts right in Canvas. So what we ended up doing, we just take the text and we pick a much, much larger font size, something like 50 times larger, and then we measure the text with a larger pixel size, and then we divide it by the p-multiplication factor. This is not exactly precise because hinting can cause different text measurement, but it's closer to the truth than if you just use the direct methods. All right. A couple of things that we have to still do. There's more font and printing work to be done. We are not implementing the entire spec yet. We're interested in more backends, in particular SVG and HTML. Maybe advanced PDF features like forms and stuff like that. And automated testing is also pretty important. It's very easy, and the code size of the code base we have now is pretty easy to break stuff if you don't have decent tests. All right, demo. That's usually what people want to see anyway. So I was not brave enough to give the entire presentation this PDF.js. But you can see that we can render the entire content as well. You see a couple of rendering artifacts here and there. Many of those actually are in Keynote. So Keynote exported a bad PDF. It's not even Preview can actually read. But it roughly looks the same. And then we have a little slide out here that shows you our Preview. And this is actually using the same renderer. So if I scroll down really quickly, you can see this is all lazily rendered. So we only display a couple of these things and lazily render them. And the re-rendering is fast enough to kind of keep up with the actual scrolling. And then hopefully the network is going to work, because then I can show you this here. So this is a little demo that someone from Mozilla put together with students from this university. So this is a 3D WebGL canvas that uses PDF.js to render the content of this very first document that we rendered with PDF.js and puts in a cube, and you can rotate this around and zoom into it and whatnot. And this kind of shows the power, really, of using proper web technology. So it will be much, much harder to do something like this with a native code plugin, because you have to get the content somehow into the web stack. And if you use web technology to render these things, then it's already automatically there. All right. That's for my talk. Any questions? So there's a PDF spec. The spec tells you what PDFs are supposed to look like, and then there's reality, which is quite a bit different. That you have to reverse engineer. So there's many PDF generation tools, literally hundreds of them. And you have to kind of guess a little bit and look at different documents to really find out what the reality looks like. But the basic spec is available, and it's an ISO spec.
Probably also a basic question, but why Canvas and not DOM? Is it really performance?
We picked Canvas as the first thing. We will do HTML and SVG next. There's no particular reason. We know that Canvas is very fast for the same reason as string computation is fast. There's IE9 competed in marketing over Canvas performance, so everyone went and make the Canvas really fast. So we knew we would be very fast with Canvas. We have not investigated the other ones yet. They will probably be fast as well.
Probably solve your selection and your
Oh yeah, absolutely. So SVG is for text selection and printing, very interesting. Yeah. Sure. I'm not too familiar with ports. I know that it's roughly based on a PDF rendering pipeline, so it should be possible, yeah.
Excuse me?
Yeah? Oh, okay. So he was asking whether it's possible to render PDF-related specs like the Quartz UI rendering pipeline with PDF.js, and I assume yes.
I was just wondering, I'm familiar with PDF specifications, but I assume you dropped a lot of stuff because the other PDF reader does a lot of fancy things. How did you decide what to drop and what to do?
So the question was whether we implement the entire spec or whether we have dropped parts of it because the PDF reader is so extensive. That's totally true. So the Acrobat reader is like a 50 megabyte download or something like that. There's a ton of crap in there. There's there's 2 JavaScript engines, I think, a Flash engine or 2 Flash engines, various stuff that you don't need. That's just how the business model is. Every year they put out a new version of the reader with some more crap in it. And in reality, most PDFs on the web don't really use that. So if you look at popular readers, like the one that's in Chrome or the Preview one that's on macOS, that thing really just supports PDF 1.3 plus a few little things. So that's roughly what we are shooting for. We are shooting for compatibility with 99.9% of the PDFs you will find on the web. And that's a much, much smaller subset than what the actual spec is. So we kind of knew what the important stuff is, and from there on we're just iterating. We pick a new document that we find somewhere, with the PDF specification itself, for example, and just kind of see what features are needed and add those.
Hey, first off, this is a great project. And there are a lot of fragments in that project, like the CLib deflate decompression that would be very useful in other projects as well. Or that could work as a native code, or planning to move those fragments back to the browser as native code?
So the zlib stuff, for example, we were considering, it's still quite a bit slower, actually. So by the way, if someone interested in the code, it's up on GitHub. The zlib stuff in particular is kind of slow in the browser, and JavaScript is like 10x slower or so than native. That's something we were considering. There's also, we found also this holds in the Canvas specification. You cannot draw a dashed line in Canvas. You can emulate that, it's just really hard math. So that's something we proposed and it's already in the spec actually. Similarly, there's compositing things together in Canvas and merging images is kind of difficult. So we will use this project to kind of drive what kind of features are missing, absolutely.
Awesome.
Any other questions at the back maybe? All right.
I was really surprised that you suggested making your code uglier rather than, for example, improving the inliner for small functions. Is that a potential? Can you talk a bit more about how you do that on that side?
So I used to work in a JavaScript group, and there's a talk here on JavaScript performance and also on garbage collection performance. So there's an ongoing battle to like make JavaScript fast. That's going to take some time. JavaScript is a language that's actually much harder to optimize than a traditional like typed, statically compiled language. As a simple thing as a function call over this, it's really hard to tell where it's going. There might be a getter that just fired. You can't really see it in the code easily that somehow changed the binding of that function on this somewhere else. Or you might call it the DOM. The DOM calls an event handler that changes it somehow. So it's very hard to determine. You can do optimistic optimization. You can kind of inline and guard against not failing. These things are being done. So the next version of our compiler will do that to a degree. But right now, if you want to make it fast on current browsers, if you do a little bit of profiling and a little bit of uglification of a couple lines of code, you get massive performance gains. So I think it is worth it.
Is the eventual plan to ship this as part of Firefox?
Absolutely. So the goal for this quarter is that we want to put out an extension that you can download and install. And ultimately, we would like to see this in Firefox as well.
And which other browsers does it run in right now?
Our main focus is Firefox. That's what we know best. It runs, community contributors have ported to every browser out there. It runs really well in Safari, Chrome, and Firefox. It runs somewhat in IE9 as well. It's just really slow because they don't have typed arrays. Brandon?
So I understand one of the things that's in PDF is Flash.
Yes.
Are you going to handle Flash?
Well, so when we set out to do this project, really, our motivation was very much from the platform side. Like, we don't like plugins. Plugins crash, they're crappy, they're a security problem. So we picked kind of one popular plugin, or native code piece, PDF, but Flash is kind of the obvious elephant in the room as well. So there has also already been a project to do Flash. It's very partial, it's very small, and we are very hopeful that that project will be extended, or other projects like it will eventually replace Flash. Conceptually, PDF and Flash are really the same thing. You have commands in the stream that somehow render stuff to the screen. And I think we have proven that you can do that very effectively using the web pipeline. APIs like Canvas are very high-level, very efficient APIs to do this kind of pixel pushing. So really all you do is kind of map the high-level Flash format to a high-level Canvas format. There's not all that much heavy lifting and computation to be done in JavaScript, so you can do it very efficiently. All right. Thank you very much.